Okay, here we are again. This is Intermediate Micro Lectures on Game Theory. So, this lecture will be the basic of what is a game and what is Nash equilibrium. I am breaking the entire set of lectures into 5 parts. So in part 2, we will cover Prisoner's Dilemma example of a game and dominant strategies. Then in part 3, much more varied examples and how to use best responses to identify Nash equilibria. Part 4, we'll get into a little bit on sequential games and subgame perfect Nash equilibria. And then part 5, just a brush over auction style games and continuous best response functions. All of this is Chapter 13 material, so you can refer there for more context and a few examples, some of which I will borrow from, but a lot of which will be distinct from what I cover in the lectures. All right. So, what makes it a game? Essentially, right, game in our econ vocabulary is going to be different from game in your colloquial understanding of what is a game, right? As with many things in econ. So our broad definition and sort of an intuitive description of it, right, is going to be that a game is any strategic interaction between 2 or more players in which the benefits derived by each player depend not only on their own actions, but on the actions of their opponents or the other players in the game, where players could be any sort of entity, any sort of decision-making entity that can derive benefits, right? So that could be individuals, it could be firms, it could be cities, it could be countries, right? We can kind of squeeze many different types of interactions into the framework of breaking it down to the key actions that are available and the benefits that each player derives, right? Which is all that we're really doing here. Now, some examples of where our traditional understanding of games could be, our colloquial understanding of games could be fit into our econ framework of a strategic game. So football, right? An NFL season, right? I could consider a very complex strategic game with 32 players being the head coaches of each of the 32 NFL teams, right? Their actions being individual choices that they make in each game, and the payoffs being something to do with their own prestige and income based on how their team performs in each season. The problem with that is it's such an infinitely complex game with 32 players and who knows how many stages of interaction, where you could imagine each play made in a game being another stage of interaction between the 2 players, that the complexity is so vast that we don't get any, there is no useful implications that we could draw by trying to fit it into our strategic game setting, right? But possibly a vastly powerful artificial intelligence could go there, but not something that I'm going to try and do. Same kind of problems happens even in a much more simplistic game setting, right? We could think of 2 players in a chess match as also being a game setting, but their strategy sets of actions available to them are also so broad, and there are so many potential stages of interaction, even in a single game of chess, that it's not going to be a useful exercise to try and fit it into this type of game theory setting. However, I can, right, often distill other types of interactions between different entities into this setting where we can infer kind of important aspects of why we observe certain outcomes or what types of outcomes we might expect to observe based on the actions that are available and the benefits that we hypothesize are derived by the players, right? So the questions we want to ask are, who is interacting? Who are the players involved in a game, right? And what are their possible choices available in each stage of the game, or it may have multiple stages, right? And what are the payoffs that they're looking for? What's their objective? The objective of each player, or the incentives that they are subject to, right? And those are the three kind of main factors of what's going to define a game setting. But we can also be aware of and be sure we're thinking accurately about information if there is some sort of information asymmetry, or just what each player knows about their opponents, and rationality. What does it mean for players to be rational in a given setting? So some definitions here, right? A strategy in this setting is there is a broad and slightly more cumbersome definition of strategy for a generic game setting where we may have multiple stages and stuff, where we say that a strategy AI is a whole set of actions that player I has chosen for each possible decision node, or there may be n different decision nodes, or more than n really, for all the different stages of the game, right? Because not only in future stages does the player need another strategy, they need a strategy that covers every possible outcome at that point in the game, right? So if combinations of their own action in the first round and their opponent's actions in the first round create different possible decision nodes in the second round, then they need a strategy that covers what their choice would be in each of those future decision nodes. Good news is, for most of our purposes, we're going to be able to keep this very simple, where strategy is going to just be a single action, right? Because we're going to think about lots of static games where there is a single decision node for each player, right? So player one's strategy A1 is just going to be choose left or choose right, or choose up or choose down, or choose high output or choose low output, right? A single binary or discrete choice. And then further definition, a strategy AI is a best response, what we call a best response, if it is exactly what it sounds like. It's responding to opponent's action AK, or all of their opponent's actions, right? It's a best response if no other strategy would make player I better off. So if it's the best they can do given the actions of all other players, that's what we call a best response. Which brings us to Nash equilibrium, right? You may be familiar with the term. John B. Nash was the father of this idea, or at least the person who popularized it, where we can think of something as a Nash equilibrium if it is such that every player is playing their best response to the actions of every other player simultaneously, right? In the definition here, I tweak that a little bit by saying playing the best response to their beliefs about opponent strategies, but then all of those beliefs are correct. That's effectively the same, right, as saying that it's the best response to the strategies chosen by their opponents. In other words, every player is doing the best they can for themselves given the actions of every other player. You'll note that this is the underlying equilibrium concept to much of what we've already done in economics, right? When we talk about an equilibrium, we are essentially imposing this idea of Nash equilibrium in a variety of different ways. So in this case, right, it's very direct. Players that are choosing actions or strategies, and if those are the best actions for each individual player, given the actions of every other player, then that's a Nash equilibrium. And this Nash equilibrium concept provides us with a useful notion of consistency, because the key idea is that at that Nash equilibrium, no individual player would want to change their choice given the choices of all others. So as long as they don't have any influence over the choices of all others, then this is maybe not the expected outcome of a game, because it's possible that there are multiple Nash equilibria, but it is a potential outcome of the game that would be stable, right? And when I say game, I mean any type of strategic interaction. Finally, another useful definition is a dominant strategy, right? Where each player is choosing strategies. If for a player, we can identify a single strategy that is the best response to all of the possible choices of their opponents, then that is what we would call a dominant strategy, because it is always their best response, no matter what other players are doing. So it is the only strategy we should expect that player to choose ever, 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 right? Because it's always the best response. It wouldn't make any sense for them to choose any other strategy. And if that's the case, that's going to vastly simplify the exercise of trying to identify the potential outcomes of a game, because we already know exactly what at least one player should be choosing to do. All right, that's it for this portion of the lecture. I'll be back with the rest in part 2.